Okay, so as I said, we're going to start now developing the theory of the ideal gas using the canonical partition function. So this is kind of a big topic which will take probably all of this week to get the final answer, maybe some of next week. This is the statistical mechanics of the monatomic. So I assume there's only one atom per molecule, which means I ignore things like rotational energies or vibrational energies. Ideal gas. This is the topic, and as I said, it's quite complicated, so probably it will take a couple of lectures to get the results. So we've already worked out, just after the midterm exam, or at least I told you, what are the energy levels of particles in a gas. Single particle energy levels in a cubic box of total volume big V. And we computed these and we found that they're labeled by a vector of integers, epsilon n. The result was that the energy level is 2 pi squared h bar squared over m e to the minus 2/3 n squared. Given by this, where n is a vector of integers, 3 dimensions is nx, my, and z. Okay, and each of these is an integer. So this result is actually only true for a cubic box, where the sides are all the same length. But later on, the results we derive will be true for any shape of box. We only need to make this assumption because it makes the energy levels simpler. Later on, we'll see it doesn't matter. The shape of the box does not affect the behavior of the gas, well, unless it's a very strange shape. But the volume does. So the volume of the box is important. Okay, so that's what we've got. Now, if these were non-interacting and distinguishable particles, then we can easily write down the partition function. If there were n non-interacting distinguishable particles, then using the result we derived at the end of last time, I can write down the canonical partition function, the sum over microstates e to the minus energy of microstate kBT. And for non-interacting distinguishable particles, you can split this into a sum over each particle by the energy levels like labeled by this vector n of e to the minus epsilon n over kBT or to the power n. So if the particles were non-interacting and distinguishable, we can write down the partition function like that, and then we just calculate it and get the answers. But if you were to do that, you would get the wrong answer. And the reason it's wrong is because in a gas, the particles are not distinguishable. If I have a gas of helium, then any two helium atoms are exactly the same. I can't tell them apart. So in a gas, the particles are indistinguishable. This means that this formula is wrong. So that in a gas, the particles are indistinguishable. Okay? Non-interacting is right. The ideal gas, the assumption is that they're non-interacting. But there's a particle. But as quantum particles, they are indistinguishable. You can't tell two of them apart. Now this makes a big difference in terms of number of microstates. So this affects the number of microstates. Okay? Which means that we have to correct this equation to make it correct, to make it approximately true. Okay. So I think this is best illustrated by a couple of simple examples. And to make things simple, let's suppose I only have 3 particles. Okay, so I can specify the microstate by telling you what's the energy level of each particle. This. And let's suppose I have 3 particles. So let's suppose I have 1 particle here. Suppose I have 1 particle here, 1 particle here, and 1 particle here. Now, if these particles are indistinguishable, this is 1 microstate. This is 1 possible microstate. The indistinguishable particles, this is 1 microstate. So I'm going to shorten distinguishable, indistinguishable, just to save my arm writing so much. So for indistinguishable particles, this is 1 microstate, because you can't tell them apart. But for distinguishable particles, you can think of these then as being balls which are numbered. In this case, there are many microstates, because, for example, I could put the first one here, the second one there, and the third one there. But for distinguishable particles, the order matters. So I could also put the first one here, the third one there, and the second one there. Okay, so we've done this before in the section of combinatorics. I can do 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So for the distinguishable particles, there's many microstates for 1 indistinguishable microstate. Okay? In particular, if there are 3 particles like this, then there are 6 possible microstates. 1, 2, 3, 4, 5, 6. So for distinguishable particles, there are 6 microstates. And all of these microstates correspond to the same microstate in the indistinguishable case. Because here I can tell the particles apart, they have different numbers, but here they all look the same. So therefore the number of the microstates is different. And in particular, in this case, if the particles all have different energy levels, then the connection is quite simple. We worked it out before. the relationship between this 1 and this 6 is that 6 is just equal to n factorial. We saw that n factorial is the number of ways of arranging n objects. So in this case, we have 3 objects, and we can arrange them in 6 different ways. In this case, it's quite a simple result. Okay. But the problem is that not all microstates look like this. I can have microstates where more than one particle occupies the same level. This is allowed for bosons and for distinguishable particles. So let's look at an example like that now. Okay. So if again I look at the case with 3 particles, but now let's suppose that there are 2 particles on the bottom energy level and 1 on the higher one. So now for the indistinguishable particles, it now matters whether the particles are bosons or fermions, because for fermions, this is not allowed. For fermions, you can only have 1 particle per energy level. So for fermions, let me do bosons first. For bosons, this is okay, so it counts as 1 microstate. For fermions, this is no microstate. No microstates because you can't have 2 particles in the same energy level. Okay, and we can also look at the case for distinguishable particles. And again, there's more than 1 for distinguishable particles. So I can number them in different ways. I can have the first 2 on the bottom and the third one on the top. Or I can have, say, 1 and 3 on the bottom, and the second one on the top. Or I could have 2 and 3 on the bottom, and the first one on the top. So for distinguishable particles, this is 3 microstates. Okay, so the numbers of microstates is quite different depending upon whether the particles are distinguishable or not, and the relationship is quite complex. Okay, I get different answers for bosons and fermions, and I get different answers depending upon whether the particles are in the same level or in different levels. So the relationship between numbers of microstates is complex, and that affects the sum here, where you have to sum over numbers of microstates. So that's why this sum is only true for distinguishable particles, not true for a normal gas. So let me summarize that. The relationship is complex. The complex relationship between the numbers of microstates for the distinguishable particles and the number of microstates for indistinguishable, and in particular, it's different for whether they're bosons or fermions. Okay, so we need to find a way of getting around this problem if we want to calculate the canonical partition function. one way we can do so is the following. I said that if the particles are all in the same, are all in different levels, something like this, then the relationship is quite easy. Okay? For every one microstate for indistinguishable particles, you get n factorial microstates for distinguishable particles. So if the particles are all in different energy levels, then the relationship is quite simple. So we can get the result as long as we assume that all of the particles have different energy levels. If all the particles are in different levels, then the relationship is simple. Namely, one indistinguishable particle microstate corresponds to n factorial distinguishable particle microstates. So in this case, we can make a simple relationship between the partition functions. For the indistinguishable case, we simply have to divide by n factorial. So therefore, in this case, and only in this case, Z for indistinguishable particles is simply 1 over n factorial times Z for the distinguishable particles. Because in this sum you have n factorial microstates, and in this sum you only have 1. So you just divide by n factorial. So we can write down Z for indistinguishable particles in the case that all particles are in different energy levels. But how do we know that this is true? How do we know that all of the particles are in different energy levels? Well, one way you can do it is to go to very high energies. If I go to very high energies, then the number of energy levels is very large, much larger than the number of particles. So in this case, I can be confident that all of the particles will be in different energy levels. So at high enough temperatures, you have that the number of accessible energy levels is much, much bigger than the number of particles. At some high temperature, and you actually have to calculate what this temperature is, but I won't do that for now. But at high enough temperatures, particles can occupy a very large range of energy states. Therefore, the number of energy levels can be much larger than the number of particles. And in this case, it's likely that there's only one particle per level. Just statistically, the number of levels is so huge that you're unlikely to put two particles in the same level. So I can draw a picture of this, right, to just illustrate. Suppose I've got 4 energy levels which are accessible, and suppose I've got 5 particles. Well, then you always have more than one particle in the same energy level, right? 4 levels, 5 particles. In this case, you must put more than one particle in the same energy level. And if I go to the case where I go to slightly higher energy, so I can attain now, say, 6 energy levels, then it's possible that they all have different energy levels. Okay? It's possible that they can be like this. This is the case of 6 levels and 5 particles. But still, it's fairly likely, statistically, that you'll get two particles in the same level. Like this. So in this case, sometimes they'll all be in different levels, but sometimes you will get two in the same level. Now, if I go to a much, much higher limit, where I've got millions of levels and just 5 particles, okay, so I can't actually draw a million levels, but you get the picture. If the number of levels is enormous, then it's highly, highly unlikely that these particles will be in the same level, just because there are so many levels to choose from. And as I increase temperature, I increase the average energy per particle, and I therefore increase the number of levels accessible. So as I've drawn it this way, increasing the number of levels is increasing the temperature. So for high enough temperature, we can assume that the particles are all in different levels. And if the particles are all in different levels, then we can simply relate the partition function for indistinguishable particles to the partition function for distinguishable particles. So therefore, at high enough temperatures, we get that the indistinguishable partition function is approximately 1 over n factorial times the distinguishable partition function. Okay. Right, so I think we better finish the class a bit early, okay? So let me just summarize what we've done so far. For distinguishable particles, this Z is quite easy to calculate, and we've written it down. And we've shown that at high enough temperatures, we can relate it to the real case, which is indistinguishable particles, just by dividing by n factorial. Okay. So starting from Thursday's class, we'll start from here, and we'll calculate this to find the properties of the ideal gas. Okay. One remaining point, which I will just finish by saying, is how high is T? How high does the temperature need to be? Well, in fact, it turns out not very high. This is a good result as long as your temperature is about bigger than 1 Kelvin. So apart from at very, very low temperatures, this result is a good approximation. And in particular, at temperatures on the Earth, at room temperatures, this is an excellent approximation. So this is true. It's quite hard to show. Right? The question is, how high does the temperature need to be so that there are enough energy levels that the particles all go into different energy levels? This is quite hard to prove, and actually I won't prove it this semester. But if you take the course next semester, then I will prove it then. So if you're going to take that course, you can see it then. Otherwise, you just have to believe me. Okay? Because this proof is quite difficult. Next semester, we'll develop some more theory, which will make it easier to calculate this number. So for now, just please believe me when I say that this is a good approximation, as long as your temperature is greater than about 1 Kelvin. Okay, everybody, shall we make a start? So I'm going to continue where we were last time, which was developing the canonical partition function for the ideal gas. Okay? And we didn't manage to do it all last time, so let me remind you where we got to. The first result is that I said for distinguishable particles, distinguishable non-interacting particles, with energy levels epsilon I, we showed that the partition function Z is quite simple. It's a sum over the possible energy levels I of the Boltzmann factor to the power of the number of particles. Okay. So for the distinguishable non-interacting case, it's quite simple. Okay. But for indistinguishable particles, it's more complicated, and therefore we need to use an approximation. And what we argued last time is that for indistinguishable particles, if the temperature is high enough, then there are many more levels than there are particles. Okay? In this case, it's unlikely that more than one particle will be in any one level. And then there's a direct relationship between the two partition functions. So for indistinguishable particles, at high enough temperatures, the Z for the indistinguishable particles is approximately 1 over n factorial times Z for the distinguishable particles. So this was a result of the fact that if the temperature is high enough, then there will be at most one particle per level. And if there's one particle per level, then the number of rearrangements is just 1 over n factorial. Okay. So that's where it comes from. Okay. Now in this approximation, I told you that at typical pressures and volumes, this is good as long as temperature is a few Kelvin for a gas, for an ideal gas. So this is quite a good approximation. And this gives us, for the ideal gas, we have that Z, which is a function of temperature and volume of the gas, is a sum over nx, ny, and z, which go from minus infinity to infinity. Of e to the minus epsilon n over kBt. So the energy levels in a gas are labeled by some vector n, okay, which take integer values between minus infinity and infinity, where epsilon n is a function of v. That's where the function of v here comes from, and was found to be 2 pi squared h bar squared over m times v to the minus 2/3 times the length of the n vector squared. These are all results that we saw either last time or before that. So far I haven't done anything new. Okay, so in order to calculate this, we need to evaluate the sum, n goes from minus infinity to infinity, of this thing, which looks like e to the minus constant times n squared. Okay? Now this sum you can't do exactly. The sum e to the minus n squared you can't do exactly, and therefore we're going to use an approximation. To this one. E to the minus some constant times n squared. That's the kind of sum we've got. But you can't do it exactly. So we will use an approximation. Okay? And the approximation we'll use is one which is going to be very useful throughout the whole of statistical physics. So if you take the course next semester, we'll use it a lot then as well. It's called the density of states approximation. What we want to do in general is a sum of some function of energy over some certain energy levels. Okay? So we want to calculate a sum which looks like a sum over certain energy levels I of some function of the energies epsilon I. For some, I is just a label of index of energy levels, so in the case of an ideal gas, it's actually a vector of integers. But that doesn't matter. All it is some label for all of the different energy levels in the gas. And that's exactly the kind of sum that we want to do here, right? We're summing over certain energy levels of e to the minus energy divided by kBt. This is some function of energy. So this is what we want to calculate. Okay. Now, what does this look like then? If I draw it as a graph of the function f of epsilon against epsilon, suppose that this function looks like this, something, I don't know. Okay, in fact, it's an exponential decay, so it doesn't look like this, but this is just to give you an idea. Then, there are certain energy levels here, epsilon 0, epsilon 1, epsilon 2, epsilon 3, and so on, epsilon 4. And for each of these energy levels, I take the value of the function and I add it up. So what you do is, in this sum, you take the values of the function at each of these points and you add them all up. Right. Now, hopefully this should remind you of the picture of what you do when you calculate an integral. So let me compare this to you now. Compare with the definition of integral. If I try and integrate the function between 0 and some upper bound epsilon, then this is defined as the limit of a sum delta epsilon times the sum I goes from 0 to epsilon over delta epsilon of f of I delta epsilon. Okay. So if I draw that picture for you now, what you do in the integral is you take evenly spaced chunks like this, and you add them all up, right? Where the width here is delta epsilon. And you basically approximate the integral by the area of all of these rectangles here. Right, so I'm sure you've seen this before, right? So the idea is we're going to relate this sum, which is a sum like this, to an integral, which you can define as a sum like this in the limit that the width between states is very small. So we're going to relate this sum to some kind of integral. This is the idea of the density of states approximation. You can note that the important difference between these two cases is that here the width is fixed, right? In the definition of the integral, the width delta epsilon is fixed. Whereas here, the distance between energy levels varies. So that's something we have to take into account. Okay? Secondly, this is a good approximation provided that f changes slowly over one rectangle, over width delta epsilon. So this is good if f of epsilon changes slowly over the width delta epsilon. So let me draw you a picture to show you what I mean by that. So I'll draw two different functions of f. F1 of epsilon, 2 epsilon. So I can take a function which looks something like this. Well, okay, that's too boring. Okay. Function which looks something like this. Or I can take a function which looks something like this. Okay. Now in the first case, the sum is a good approximation to the integral, because the sum looks like this. Okay. And you can see that the area of the rectangles is virtually the same as the area under the curve. So in this case, it's a good approximation. Whereas in this case, the sum is a very bad approximation to the integral. Okay? Because the area of the rectangles is very different from the area under the curve. So this is why I say that f has to change slowly. If s changes fast over the width delta epsilon, then you can miss some of the important changes in the function f, and therefore you'll get errors. Okay. So in order to rewrite the sum as an integral, it's important that the value of the function f does not change significantly in between energy levels. Right. So this is what we hope we can find. So suppose we can find an energy scale delta epsilon such that, firstly, this is true. So firstly, it's good enough to give you an integral, well, an approximation to the integral. So f of epsilon changes slowly over delta epsilon. Okay, and I should say, sorry, this is a bad approximation, right? So firstly, we want to find a scale where the change of f is slow over that scale. And secondly, we want to find a scale such that there are many energy levels within a particular width. Okay. Okay, so I want these two conditions to be true. Firstly, this width is such that the function f changes slowly. And secondly, within this width, delta epsilon, there are many energy levels. Then in this case, we can approximate the sum over energy levels with an integral. Okay. So we can define this as a function. We set the number of energy levels between epsilon and epsilon plus delta. as some function which depends upon epsilon times delta epsilon. If I draw this again as a graph, here's my width delta epsilon. I'll draw it bigger now so you can see it. And we suppose that within this width we have many energy levels. Okay. So these red things here are energy levels. Okay. So for example in here, as I've drawn it, there are six energy levels within a particular width delta epsilon. Here and here. Now this function rho of epsilon is called the density of state. And it's what gives this approximation its name. Then we can say the following is true. The original sum that we wanted to do is approximately equal to an integral of the function f, except that instead of just taking one sample per width delta epsilon, we take many samples, because we take one value for each of the energy levels. So therefore, we have to multiply by the number of energy levels, which is just rho of epsilon. Okay. So if we just take one sample per width delta epsilon, we just get an integral of f. But if I take many samples over a width delta epsilon, then I have to multiply f by the number of samples I take, okay, which is this. Okay, so this is the result, and this is called the density of states approximation, and as I said, it's quite important, and we will use it frequently for the rest of the course. So in order to use this approximation, we have to calculate what is this function rho, so what is the density of states for the ideal gas, so that's what I'll do next. So density of states for an ideal gas. So just to remind you again, epsilon n was 2 pi squared h bar squared over m times v to the minus 2/3 times n squared. Okay, let me just write it that way. Where the vector n is a vector of integers in 3 dimensions, nx, ny, and nz. Okay. So I can draw this, I'll draw only 2 dimensions because otherwise it gets too complicated. But we can draw all of these vectors in 2 dimensions. I'll take nx going this way and ny going this way. Then we get a level when both of them are equal to 0. We get a level when one of them is 0 and one of them is plus or minus 1. This is 1, minus 1, minus 1, 1. And so on, okay? So they fill up the space as a regular square grid. Okay, so in 3 dimensions it will be a regular cubic grid. Okay, so each of these blue dots is a given level for the ideal gas, for a particle within the ideal gas. Now the energy just depends upon the length of the vector n, right? The energy just depends upon n as the length of the vector. So vectors with a shorter length in here have less energy, and vectors with a larger length have more energy. So what I need to calculate is how many levels are there between two particular values of energy. So for the first value of energy, epsilon, let's say that is somewhere here. It defines a circle, right? All of the states with a fixed value of energy define a circle, like this. So I can call this distance r of epsilon. Okay, we can work out what r of epsilon is for this formula. R of epsilon is the length of all the vectors which have energy less than epsilon. So from this formula we get that r squared is equal to, okay, let me do it slowly. We get that epsilon is equal to 2 pi squared h bar squared over m, v to the minus 2/3 times the radius, the length of the vector r squared. So this means, if you rearrange it, that r of epsilon is, well, I can write it this way, 2m to the power of a half divided by 2 pi squared h bar squared, 2/3 times d to the power of a third times the square root of epsilon. So I've just rearranged this. So all of the vectors which have energy epsilon will have a length equal to this. Okay. So therefore they will fall on this circle in the diagram I've just drawn. Now for the density of states, what we need to know is how many states are there, how many levels are there between two close values of epsilon. So I take one at r of epsilon, and then I take another circle at a slightly larger radius, like this. So this radius here is r of epsilon plus delta epsilon. And I need to count how many states are within this spherical shell. So the number of states with energy less than epsilon, this is the same as the number of states with the length of n less than the radius r. Okay. So that means counting the states within this circle, the number of states within this circle, but each of these states occupies a volume of 1, right? Because this is 0, 1, 2 in both directions. So each of these states occupies a volume of 1. So therefore the number of states is approximately equal to the volume of the sphere. So this is approximately equal to the volume of the sphere of radius r. Okay, and this is again a good approximation if r is big. We'll show later that r is big in the case of gas. If r is large, then the number of states is approximately the same as the volume of the sphere. And you know that the volume of the sphere is 4/3 pi r cubed. Okay, and r is a function of epsilon. So the number of states is approximately given by this, where r is given by this function here. So therefore, the number of states between epsilon and epsilon plus delta epsilon, this is the thing we actually want to calculate, this is the density of states, this must be equal to the difference in the volumes of spheres of radius r plus epsilon and radius r. So this is approximately equal to 4/3 pi r epsilon plus delta epsilon cubed minus 4/3 pi r epsilon cubed. And we've already defined the number of states between these energy values as equal to the density of states times delta epsilon. Right? So this must be equal to the density of states, rho of epsilon, times delta epsilon. But you can see that this is just a derivative, right? The definition of a derivative is function at, well, x plus delta x minus the function at x divided by delta x. Sorry, this is delta epsilon, not delta r epsilon. So therefore, rho is just a derivative of this function here. So the density of states is just d by d epsilon of 4/3 pi r epsilon cubed. Right. If I just divide both of these by delta epsilon, here I get a derivative, which is this, and here I just get rho of epsilon. Okay, so this is what we have to calculate, and I've written the formula for r of epsilon over there. So let's just do this. This is d by d epsilon of 4/3 pi times r cubed. So we get 2m to the 3/2 divided by, going back over here, I've made a mistake, right? Going from here to here, I must take a square root. So pi squared h bar squared should just become pi h bar. Right? Going from here to here, I've taken the square root, so the squares must go away. Right, okay. So then it should work. So now on the bottom I have 2 pi h bar squared, h bar cubed, sorry, times v times epsilon to the 3/2. Okay, and if I differentiate epsilon to the 3/2, that gives me 3/2 times epsilon to the 1/2. So this is 3/2 multiplied in here gives me just 2. So this is 2 pi 2m to the 3/2 divided by 2 pi h bar cubed times v times epsilon to the 1/2. And we can simplify this, cancel some pi's and so on, and we get the final result. Rho of epsilon is 2m to the 3/2 divided by 4 pi squared h bar cubed times the volume times epsilon to the 1/2. Okay, so this is the formula for density of states for an ideal gas. Finally, we have to check that the density of states approximation is valid. That means we have to check that over the width for which the function f changes, there are many, many energy levels. Okay. So, for the ideal gas, the function we want to use in the density of states approximation is just the Boltzmann factor, is e to the minus epsilon over kBt. Okay. And this function changes with a characteristic width of kBt. So f changes significantly on the scale of kBt. And I'm going to work with the ideal gas at standard pressures and temperatures and so on. So if we evaluate this at 300 Kelvin, then this turns out to be a scale of about 4 times 10 to the minus 21 joules. Okay. So in order for the density of states approximation to be valid, we need that the distance between energy levels should be much, much less than this. So let's check that this is the case. Okay, let's check that there are many energy levels within an energy scale like this. We can do this in the following way. The average value of energy is just equal to the total energy of the system divided by the number of particles. Right? And for an ideal monatomic gas, this is 3/2 n kBt divided by n. Okay, n's cancel. So you get the average energy per particle is about 6 times 10 to the minus 21 joules. So now you can work out what is the density of states at this average value of energy. This is how many states per unit energy, right? This is the number of levels per joule. Okay. So in order to calculate this, we have to make some assumption about the volume, right? Because the density of states depends upon the volume and the mass. So, for example, if I take mass as being the mass of helium, helium is a good example of an ideal monatomic gas, and I'll take the volume as being 1 meter cubed, which is a reasonable size of a gas. Then, if you do the calculation, you calculate this thing, you find that the density of states is 2 times 10 to the 51 per joule. Okay. So this means that there are 2 times 10 to the 51 levels per joule, which means the average width between levels is 1 over this, right? So therefore, the average delta epsilon between levels is 1 over the density, which is about 2 times about 4 times 10 to the minus 52 joules. Okay. And you see that this is much, much less than the characteristic scale over which the function changes. Okay? The characteristic function scale over which the function changes is 4 times 10 to the minus 21 joules, but the average width between energy levels is 4 times 10 to the minus 52 joules. So there are many, many energy levels over the scale for which the function changes. So that means our approximation is valid. 4 times 10 to the minus 52 is much, much smaller than 4 times 10 to the minus 21. So therefore, there are many levels in the width delta epsilon over which f changes significantly. Okay. And therefore, the density of states approximation is good. So today I've introduced what the density of states approximation is. We've calculated the density of states for the case of the ideal gas. And finally, I've proved that for an ideal gas at room temperatures and reasonable sized volumes, this is a very good approximation. So we can make use of this approximation. So finally, to finish, I'll write down the equation which we will solve next time. Okay. So therefore, for the ideal monatomic gas, Z, we said at the start of this class, was 1 over n factorial times the sum nx, sum ny, sum nz of e to the minus epsilon n over kBt to the n. We can now use the density of states approximation, okay, which in general I will abbreviate to DOS approximation. So that enables us to replace this sum with an integral over the density of states. So this becomes 1 over n factorial times the integral from 0 to infinity of the density of states, rho of epsilon, which we've calculated, times the function, which is this, the power n. And then finally, if I put in the formula that we've worked out for the density of states, this is 1 over n factorial times, let's take all the constants outside, 2m, 3 over 2, b over 4 pi squared h bar cubed times the integral from 0 to infinity of epsilon to the half e to the minus epsilon over kBt, all of this to the power n. Okay, so it's a bit of a beast of an equation, but we will simplify this next time, and we will show that from this equation we can derive all of the properties of the ideal gas. Okay. Now we're going to finish what we have started quite a long time ago, and this is calculating the properties of an ideal gas from the partition function. So last time we got our final expression for the partition function. But remember that we use some approximations. We've assumed that temperature is high enough that particles are mostly in different energy levels, and temperature is high enough that we can use density of states approximation. So this is really a high T answer, and we use the density of states approximation. Remember, I told you that high T in this case doesn't really mean very high. It means greater than about a Kelvin. Then Last time we derived the partition function z, which is a function of t and volume, as 1 over n factorial times 2m to the 3 over 2 times volume divided by 4 pi squared h bar cubed times the integral from 0 to infinity of epsilon to the half e to the minus epsilon over kbt. The epsilon all to the power n. So I think this is the last equation I wrote down in the last class. So you see here various terms. We've already worked out the volume dependence. Okay, this comes from the density of states. This 1 over n factorial is from the fact that the particles are indistinguishable, and this integral is from the density of states approximation. Okay, so to complete this, we need to calculate what this integral is. So I can change variables here. If I make a new variable u, which I say is epsilon over kbt, so then du is d epsilon over kbt, then this integral becomes kbt to the 3 over 2. I get 1 kbt from here, and another one from the epsilon to the half. Then I get the integral from 0 to infinity of u to the half times e to the minus u du. Okay, this is important because we've now pulled the temperature dependence outside of the integral. Right? Here, we had to integrate, and the thing we integrated was a function of temperature. But here, the temperature dependence is outside the integral, and this, whatever it is just a constant. So it's just a number, which we have to calculate. And in fact, I will prove for you now that this number turns out to be the square root of pi over 2. So I'll prove this now, and in doing so, I'll talk about an important function, which we will use several times from now on, which is called the gamma function. Okay, so the gamma function, you may or may not have seen before, is very common in statistical physics, so it's worth going through it in some detail. And it's defined by integrals which look like this. Gamma as a function of z is defined as the integral from 0 to infinity of some number u to the z minus 1 times e to the minus u integrate du. That's definition. So you can compare these two integrals, and you see that here z minus 1 is equal to a half. So therefore, this thing we've got here is the gamma function at 3 over 2. So this has some important properties, which I will state and prove for you now. The first thing is that gamma over half is equal to the square root of pi. The second thing is that if I take gamma as z plus 1, this is the same as z times gamma of z. It has this property. And you see, as a consequence of this property, therefore, gamma of 3 over 2, I take z equals a half in this formula. Gamma of 3 over 2 is a half times gamma of a half, and I've already told you that gamma of a half is root pi. So this is therefore root pi over 2, as I told you it was down there. So these two things here are enough to give me the answer for the ideal gas. But sometimes we get these integrals with different values of z, so I'll prove one more property, which is actually very easy. Gamma of 1 is equal to 1. And as a consequence of this and this, we get that gamma of an integer n, this is n minus 1 times gamma of n minus 1, which is n minus 1 times n minus 2 times gamma of n minus 2. And if you keep going, you can get all the way down to 1. If you keep going, then this becomes n minus 1 times n minus 2 times all the way down to 2 times 1 times gamma of 1. The gamma of 1, I've told you, is equal to 1. So therefore, gamma of n is equal to n minus 1 factorial. That's another very useful result. So this gamma function can be seen as a generalization of the factorial function to non-integer values. So the proof of these statements is all easy. In fact, we've done most of the work already. So let me just prove it for you. The first one is gamma of a half. Okay? Well, gamma of a half is defined as the integral from 0 to infinity of u to the minus a half e to the minus u du. Okay, that's from the definition. Now I can make another change of variable. I'm going to say that u is y squared. So this means du. Okay, let me write it the other way around. That's correct, but I can instead write it this way. I'm going to take y as the square root of u. So this means dy is y is u to the half. It's all the same thing. So therefore dy is a half times u to the minus a half times du. That's good because you see u to the minus half du is what you've got here. So therefore this becomes twice the integral from 0 to infinity. This just becomes dy, and e to the minus u is e to the minus y squared. But this integral is symmetric, is even in y, so this just becomes the integral from minus infinity to infinity of e to the minus y squared dy. And this integral we've already done. We did it when we calculated the normal distribution, and we showed that it was equal to square root of pi. So this last part, you just see the notes on the normal distribution, where I proved this result. Okay, so anyway, now we can use all that stuff to put in this equation and see what we get for z. Z t of v is 1 over n factorial times 2m to the 3 halves v over 4 pi h pi squared h bar cubed times kBt 3 over 2 times this gamma function, which, as we said, is the square root of pi over 2 all to the power n. And lots of things simplify here. Okay. Here I've got 2 cubed is 8 square root, so this is square root of 8, and on the bottom I've also got 8, so that gives me 1 over the square root of 8, so I've got m kBt from here over 2 pi. I also get pi to the 3 over 2. H bar cubed I can write as h bar squared to the 3 over 2. So all of those terms just give me that, and what I'm left with is V. And this is our final result for the ideal gas partition function at temperatures of a few Kelvin and above. So it was quite a long journey to get this result, but that's what we find, and now we can see that it does indeed give the properties of the ideal gas that we assumed in the first half of the course. So, what can we find? We'll do a bit more. First of all, we can check the internal energy equation and see that that's right. So, as I told you, the equation here is that it's kBt squared times d by dt, the log of z. And it's worth splitting this log of z into various different terms. First of all, I've got 1 over n factorial, and the Stirling approximation tells you that 1 over n factorial is approximately minus n log n plus n, so that's minus n log n plus 1. Let me do it as a plus. So the Stirling approximation for this is going to be minus log n plus 1. Then I've got the log of all this stuff. So first of all, I get log v. Then I've got the log of all these constants to the power 3 over 2. So that gives me 3 over 2 log m kb over 2 pi h bar squared. That's just a lot of constants. And then finally, I've got log of t, also to the power 3 halves. So I get plus 3 halves log t. So all in square brackets. Okay, so that's that. And you see, when I differentiate with respect to t, the only term that depends upon t is the final one. So therefore, I get that u is n from here, kbt squared times d by dt of only this last term here, which is 3 halves log of t. Derivative of log of t is 1 over t, so that cancels one of the t's here, so I get the final result, u is 3 halves times m times kb times t, which is exactly what I told you it is. In the first part of the course, when I defined an ideal gas, I wrote down 2 equations of state, and this was one of them, for the monatomic ideal gas. So that shows you I was right. The result I showed you was true. Okay? The ideal gas does indeed have internal energy given by this equation. The other things we want to find are Helmholtz free energy, pressure, and entropy. So I'll find those 3 things in that order, Helmholtz free energy, and then we'll take a break. so the definition, well, not the definition, but we showed for the Helmholtz free energy that in the thermodynamic limit is equal to minus kBT times the log of the partition function. Therefore, F simply from that equation is equal to minus N kBT, and I'll simply join some terms together. Shall I? Maybe not. I'll do it later. Minus log of N plus 1 plus log of V plus 3/2 log mkb over 2 pi h bar squared plus 3/2 log kBt. Okay, so that's an equation, quite a long equation, but not particularly complicated for the Helmholtz free energy. Okay, we can also find the pressure. P is defined as the change of energy minus the change of energy with respect to volume. That's just the work done. Like P times V is equal to the work done, so that's minus change in energy. This is when you're at constant heat, at constant entropy. And we proved that differentiating U with respect to differentiating U at constant entropy is the same as differentiating F at constant temperature. Minus sign stays there. So I need to differentiate this equation with respect to V. You see that there's log V, so this just gives me 1 over V. Minuses cancel, and I get that this is N kBt times 1 over V. And you see that simply you can rearrange this equation to get it in the familiar form. PV is equal to N kB times T. So this is our second equation for the equation of state for the ideal gas, which I told you many weeks ago. And you see that again it's right. So our statistical mechanics, our theory which told us how entropy is related to the number of microstates and so on, predicts the correct behavior for the ideal gas. We get these two equations of state, which I gave you at the start of the course. Right, so I think that's a good place to take a break. The final thing we haven't calculated yet is the entropy. So after the break, I'll calculate the entropy and then we'll summarize the ideal gas derivation. Okay. But what we've done now is very important. At the beginning of this course, I just gave you these two equations as empirical results. I said, if you look at a gas, you get this result and this result. But now I've shown that you can derive these results theoretically from statistical mechanics, from the idea that the entropy of a system is related to the log of the number of microstates it has. So this is a very important result to finish. Okay, so let's continue from where we were before we took the break. So we've nearly finished deriving the properties of the ideal gas. And in fact, I've shown the two equations of state, which I told you before, the ideal gas. But we can also calculate something new to us, which is we can use this equation to find the entropy. So the entropy, one of the other equations I proved last week, is that the entropy S as a function of temperature is equal to minus the derivative of the Helmholtz free energy with respect to temperature. Okay. If I differentiate that equation with respect to temperature, I will get the entropy. Okay, well, that equation is quite easy to differentiate with respect to temperature. The T outside just gives me n kb times all of the stuff in those brackets minus log n plus 1 plus log b plus 3 halves. It's exactly the same. Okay, so it's up to you whether you want to write it all out again or not. All that stuff. Okay, that's one of the things. Or we can differentiate this t, which will give me 1 over t times 3 halves. So then t's cancel, and I just get plus 3 halves n ab. Okay, so that's quite a complex expression. It can be written in a simpler form if we make some definitions. First of all, n over v, this is the number of particles per unit volume. So I'll call this little n, which we can call the particle concentration. Number of particles per unit volume, particle concentration. And then I can combine these things into another constant, which is called the quantum concentration, but note it's a function of temperature. Okay. And if I make these definitions, then this equation is very much simplified in terms of its writing, at least. This becomes n kb times the log of nq over n plus 5 halves. We can note some interesting things about the entropy. The first is true in general, actually. The entropy is always proportional to the size of the system. So S scales proportionally to the number of particles. Its temperature dependence comes in here, Qt, and you see that this is like T, like log of T. So S is proportional to log of T. And from this equation, that means it's proportional to the log of the internal energy as well. So entropy looks like log of U times some constant for an ideal gas. And finally, it's okay. Proportional is not actually true, right? Because you've got a constant term here, so I shouldn't write this. What I should write is it grows like. A more vague definition. It's strictly speaking not proportional because you've got a constant there. But its rate of growth is log of t or log of u. And in the same way, S goes like minus log of n. So increasing the density, that means compressing it, decreases the entropy of the system. Okay. Now, you should note that this equation cannot be quite correct at all temperatures. If I call this equation star, note that as temperature goes to 0, star diverges. The entropy goes to minus infinity. The reason the entropy goes to minus infinity is because here you've got log of t, and log of 0 goes to minus infinity. Right? So it goes to 0 because of the log of t term in the entropy. Okay. But you know this cannot be correct because as temperature goes to 0, the system goes into the ground state, and the ground state is unique. So there's a single unique ground state Therefore, it has zero entropy. So as t goes to 0, the system goes into the ground state. And the ground state is unique, and therefore it has zero entropy. The ground state is unique. This means that S, which is defined as Kb times the log of the number of microstates, well, there's only one microstate because it's unique, so this is Kb times log of 1, which is 0. Sorry to write at the bottom of the book. But in fact, this is generally true. Ground states are almost always unique, and therefore the entropy of the ground state is almost always 0. So for virtually all systems at 0 temperature, the entropy should become 0. So that means that there's a problem with this equation at low temperatures, but we already expected that because we've made approximations which assume that the temperature is high, and we assume that the particles are in different energy levels. So, this is a summary of the ideal gas calculation. It was quite long, it had lots of different ideas, and all of these ideas are important in statistical theory, so let me go through it step by step. What we started with was the quantum solution of a free particle in a cubic box. Okay. And we showed that the energy levels are labeled by a vector, and in particular, they were 2 pi h squared over m c to the minus 2/3 times the length of the vector n squared. So this was the first result we had. We modeled a gas as lots of free particles in a box, and we calculated from quantum mechanics that the energy levels were this. And note that this result depends quite strongly on the shape of the box. So in fact, this result is only true if the box is a cube. If I take a different shaped box, I will get different results. This result depends on the shape of the box. So that was the first point. The next part was we developed the theory of the canonical partition function, and we said that if the particles are non-interacting and distinguishable, it's quite simple. The partition function for non-interacting, distinguishable particles so this was Z is sum over possible particle states, which are labeled by these vectors n. So sum over all possible n of e to the minus epsilon n over kBt. Number of particles, we proved this result. Particles are non-interacting and distinguishable. You can just sum over the single particle state and take it to the power of n. But in a real gas, the particles are indistinguishable. So our next thing we did was to say that really the particles are indistinguishable. And there you can't calculate the partition function exactly because the number of microstates depends upon whether the particles can occupy the same state or not, and so on. But we argued that at high enough temperatures, they should all be in different states, and then we can just divide by n factorial. So at high enough temperatures, this was the first time we made an approximation, then we can get it just by dividing by n factorial. This. And I told you, although I didn't prove it, and I will prove it next semester, that for an ideal gas, high enough T means about above a few Kelvin for this approximation to be valid. Next, we had to evaluate this sum. But you can't evaluate this sum exactly, because this energy epsilon goes like n squared, so you get a sum of n e to the minus n squared. You can't do that exactly. So we use the density of states approximation, where you replace the sum by an integral. Okay. And this is what we did last week. We calculated the density of states of epsilon as being 2m to the 3 over 2 times b divided by 4 pi squared h bar cubed times epsilon to the half. And this result does not depend strongly on the shape of the box. So in fact, to derive this result, we assume that the box is cubic, but you can show that whatever box shape you take, as long as it's not incredibly small of quantum size, this result is generally true. So this result does not depend, at least not strongly, on the shape of the box. And using this approximation, what you do is you replace the sum by an integral multiplying by the density of states. And this is what we did today. We said that this tells you that z is 1 over n factorial times the integral 0 to infinity with the density of states times e to the minus epsilon over kBt. D epsilon to the power n, and this is what we did today. Today we evaluated this integral, and we got the final result that this is 1 over n factorial times n kBt over 2 pi h bar squared 3 over 2 times b all to the power n. And then finally, we use various equations to find the equations of state. And so that's the end of the summary. I should say, because I forgot to mention it at the time, this equation has a name, this one for the entropy. It's known as the Sackur-Tetrode equation. Just named after the people who first calculated it. so this is a summary of everything we've done for the ideal gas over the last probably 3 weeks or so. And the form is general. Okay? So although these results, these equations are particular for the ideal gas, the calculation, the method we use is quite general. So we will, in various applications, both for the next couple of weeks and next semester, we will use the same kind of methods. The methods are, first, find the quantum states. Okay? If it's a non-interacting system, find the energy levels of the particles. Then, calculate the partition function, like this, okay? Using approximations if you need. Then, calculate density of states to replace the sum by an integral, which you can do. Using this, find the final form of the partition function, and then calculate what you want, energy, pressure, entropy, using these equations. So, although the calculation is particular for the ideal gas, the ideas are quite general. And in particular, the idea of writing down the partition function like this, calculating density of states like this, we will use a lot. So these are important. Right, so that's it. That really is it for the ideal gas. The translational part. So what we're going to look at for the rest of the course are the rotational and vibrational parts of the motion.